哎呀，俊为什么没有这么跑掉？俊伟是叫俊伟，
哦，你看到他没？
没有看到他，他有在
有在这边，啊，他现在也在这边。
他也在这边
哎，他左边了。
讲
他跑了，他跑了，
哦，他要跑
要跑要跑，现在还做退学手术。
哦，他是几时决定的？
哦，
他是几时决定？
上一个年假几时啊？
那时候他回去啊，然后回来，
就回来，要要跑去有一波呢。
啊，金宝，没有他的 hardware 坏掉，他每次要调啊，
必须。
他问题是他
了，
对呀，他又不开哦，
可以开吗？等那个学生
人家偷掉，
高，你的父母还在。
还在哦，
哇，
今天还在，
明天坐飞机走。也是一玩那种。那个不行，我去嘛。
没有他的 hardware 坏掉，他要调每次。
电视剧还有要讲是吧？那个啊，对对对，因为他也是要假如说比管子大过比 N 这个，只用 decreasing 这个来表达。那考试的时候也是要 program 这个方式是 decreasing 的。
嗯，对，
会雷没尾。
先讲，你不能的话，你不能够用这个东西。
那我知道，不是讲要用这个 pen 的时候嘛，很不方便。可是然后要用一整个 test 的时候，我认定两个题要用一个，我就 continuous 那个还好啦。 一定就是像你要做 FX 这种行业去啊，对不对？只能这样了啊。OK，谢谢。
努力
叫
这个麦过来，
刚结束的，
放吹帽子的手啊！
啊，
太阳大，
太阳大它不黑了啊，
那是怎么回事啊？我今天不来，
不知道它能跟一样，整个天呢，好像不是走的，
那讲要7点半就来了。卖，
卖，可以上去，
卖，啊！
可以办法，卖，对，反正未来有上课的时候，
有问题啊，应该8点就要来。
2点教10点，
先教师节啊，对啊，教师节怎么？Thank you，
要10点来的，
thank you。
要10点早班吗？
早班，对啊，
2个小时，可以的，
2小时，2节课。
2点好了，
对，
啊，你7点的，
来，出来，来。哎，你喜欢看《顽皮》吗？你看《顽皮》吗？哦，OK，
哇，好，好专业，哎，完了，今天是夜播日，
对，
哎，老师。哦，这 A 掉后来了，哦，为什么讲？加那你动的，你先给他8点的话，这样3块就10点，
讲他们7点半上班。我看3个礼拜还回一个这个完全帮不上忙。
哎，后面还有我们看可以问他没有来帮我写掉的太多。
哎，hello，麦坏，OK，thank you。
还有熟练，
我也是绑的，
哎，也不是偏
哪里？等一下，
还跟我讲的，也是这样，没错，很短很长时间，然后就你要跟他讲嘛，他做完做一半了，是我做完了啊，我问他哪一个比较轻，
多少多少，我算了，所以我是跟我。
没有感觉到，这样这样，
玩乐兄弟。
都不完全。反正跟我讲很简单哦，那时候昨天一回到我的时候，还是简单点。因为我之前刚讲的样，2我做做到3点的时候，然后我就跟发现有做。啊，这个做到，我这个做到了，可是我当天。做完那个还没到我的那段不知道对不对，他答案是就是我自己找到我没有这题哦，没有，
你是做这个的吗？
没有这题哦，
你编织啊？
对
，OK，
破一个放破一个。
他这个要每次调啊，这样。对，货还没到。玩乐兄弟。对，对，OK，Thank you。Hi, good morning. How's your weekend? Why? Christmas. Okay, never mind. Work harder. You get 100 in the test. Okay, for those who haven't get your quiz back, right? You can email me. I'll take a photo for you. For those who take 15 marks and below, please work harder. And then if you have any question, just feel free to email me, message me, okay? Or see me in the office hour. All right. Okay, so today we plan to finish our series in this 3 hours. Hopefully we can finish it. And then on Thursday, maybe I'll pick some revision question to do together. And then briefly run through Fourier series. Fourier series won't be tested, so I think we will, yeah.
所以考啊，所以要抄吧。
Yeah. Yeah.
So
I mean, the exam venue is in LY2 second floor. Okay. Sorry. LY3 second floor. Second floor. Later I will send out an announcement again. Okay, so don't be worried. And I also will send out the formula that was given in the exam. Okay. Huh? Power series. Taylor series. Yeah. I mean, late. I mean, Fourier series is not tasted. We will cover it Thursday. And Thursday we will do some other revision question. So everything up to okay, let's see how where we finish today. Okay. Okay, so today we will start power series. Definition of power series is a series of the form of a linear combination of monomial in X. Okay, so C naught. So let me write down. So first term is the degree zero term, which is a constant. Okay, and then a degree one term or a linear term, and then degree two term, which is a quadratic term, and then so on. Okay. So a power series in X is a series of the form of linear combination of scalar multiple of power of X. Okay. Yeah. One thing I want to say is please don't just focus on copying, right? Okay. So just listen to what I say and then see if you understand, because I will also post out the lecture note. I want to remind you that our course, right, the second half will get really hard. Okay, hard in concept, hard in imagination. Okay, so you really need to listen to what I say. Don't just copy bunch of numbers down. Okay, they don't make sense. Okay? What I say makes sense. Okay, so you need to try and imagine. Okay. Yeah. Okay. So this is a power series. So why we are interested in this power series here, right? Okay. So why were we interested in this power series? So you can see that there are sequence here, right? What's the sequence here? Okay, if we let's look at this power series here. So example of power series. So let's put an example. Yeah, let's look at this example here. So this is an example of power series. Okay, where the constant are just 1. Okay. So inside here, you can see a sequence of power of n. Okay, but why we put x here? Okay, why we put x here? So x here can be replaced with any number you like. Okay, so what number does this series make sense is the question we want to answer in this subtopic here. Okay, in this section here. Okay, so let's look at this example here. So for what x does the power series converge, and what is the sum? Okay. So I think we addressed this question before. Remember we studied the sequence of r to the power n. right? R to the power n. So now it just changed to x. Okay. So what's this x here really? What kind of series is this? This is a geometric series. Why is it a geometric series? Because an plus 1 over an, which is the ratio, is just x. Okay. And then with the first term equals to 1. Right? Okay, first term equals to 1 ratio will equal to x. Okay, this is a geometric series, which is a series of geometric sequence. Okay, so we know that, what do we know? When does the geometric series converge? If and only if the absolute of the ratio is less than 1. Okay, good. Okay, so what's the sum of these geometry series? Okay, geometry series have a formula, right? What's the sum to infinity formula? A over 1 minus r. In this case is 1 minus 1 over 1 minus x. Okay, so what does this mean? This means that our infinite sum here is equals to 1 plus x squared plus x cubed plus x4 plus to the infinity is equal to 1 over x. Okay, but this equal here is only true when the infinite series converges. Okay, so this is true only when the series converge. The series converges. Okay, so you can see that right, the left hand side here is an infinite sum of power of x, and then the right hand side is a closed form of a function. Okay, so if you still remember linear algebra, right? Okay, so what we are doing is we express this function in terms of basis of power of monomial in x. But this is an infinite dimensional, so we can do it infinitely, many bases. Okay. Note that this equality here is true only when the infinite series converges. Okay. Outside the range might not be equal. Okay, yeah. Okay, you need to remember this. Don't simply put equal sign, right? Okay, please don't simply put equal sign. So whenever this infinite series present, you need to tell me where it is true. Okay, let's see more examples. Okay, next. So you're given another infinite series here. So for what values of x does this series converge? Okay. So what to do? So what we can do is we use the ratio test. Ratio test again. So that's why I say ratio test is very powerful. So it's also very useful here. So when does the ratio test, what does the ratio test tell you? Limit n to infinity of what? Absolute value of an plus 1 over an. Okay, you want this thing to be less than 1. Okay, strictly less than 1. Greater than 1, the series diverge. Okay, equals to 1, the series inconclusive. Okay, you don't know what happened to the series. All right, So let's see. So this, you can see that this condition here will give a condition on x. Okay, so what is s? What is an here? An here is x to the power n over n plus 1 to the power n. Okay. Okay, so note that this x here, right, you can really substitute any value in. But when does this x give you a convergence sequence? We use ratio test to find. Let's do it. Okay, so what's this value is? This value is x. Right. Okay, so this, right, this one cancel, this one cancel. We're left with n plus 1 over n plus 2. Okay, so you want to make sure that this number here is less than 1. Okay. So can we get rid of this modulus here? How? N is always positive, right? Okay. So n plus 1 over n plus 2 is always positive. But s, we don't know. So we need to put the modulus back on x. So what we left with is modulus x over 2 times n plus 1 over n plus 2. This is less than 1. Okay. So is this less than 1? Or when is this less than 1? So when is this less than 1? So you can see that this limit here, okay, does this x has anything to do with the n? No, right? Okay. So we can just pull it out from the limit. Okay. Then we need to compute what is the rest. So we can rewrite this become 1 plus 1 over n over 1 plus 2 over n. Okay. So by ratio test, the series converges only if this whole thing is less than 1. So this gives us what? This gives us that x have to be in between -2 and 2. Okay. So this gives an as condition on our x. Okay. So let me write. So what do you have? So by ratio test, the series converges. Does it converges absolutely or not? Huh? Yes, sir. Is it? Why no? What's the ratio test? That's okay, so absolute ratio test says what? Okay, if the absolute value of an plus 1 over an converge to L, where L is less than 1, the series converges absolutely. Okay. Not only converges, but also converges absolutely. Okay, so converges absolutely be for x in between -2 and 2. Okay. So what happened at -2 and 2? Exactly -2 and 2. What happened? what happened to the limit? The limit is just 1. Okay, so from ratio test, it is inconclusive. Okay, but we can check it directly on that point. Okay, let's check it on these 2 points here. Okay, so let's check. Okay, from ratio test and x equals to -2 or 2. Okay, the limit of x over 2 of m plus 1 over m plus 2 is equals to 1, which means, which implies, that the test is inconclusive. We do not know whether the series is, we do not know the convergence. Okay, we do not know the convergence of the series at equals to -2 and 2. Okay, but we can check. We can check directly. So let's check what happened at x equals to -2. Okay, so when x equals to -2, what happened to the series? Okay, it becomes -2 to the power n over m plus 1 times to the power n. Okay, so what is this? What is this? You get a alternating series of n plus 1. Okay, what is this? Okay, I'm just simplifying this fraction here, right? Okay, so what's this? Anyone recognize this pattern here? The first term is, what's the first term of this alternating 1 over n plus 1? The first term is just 1, right? And then second term is minus a half, right? And then plus a third, minus a fourth. What's the sequence here? This is an alternating harmonic series. So does it converge? Converge, right? Okay, harmonic series diverge, but alternating harmonic series converge. So it converges absolutely or conditionally? Conditionally, okay? Because the absolute version of it diverge. And so this converge as an alternating. So how to check, just a test for you. So how to check alternating harmonic series converge? That's all. Okay, so you use the alternating series test, right? Okay, so you use alternating series test to test that alternating harmonic series converge. Okay, how about at the other endpoint? What happened? Okay, so can you anticipate what's happening? What's this series become simplified to? 1 over n plus 1. So what's this? This is the famous harmonic series. Okay, so it just now as what we discussed, this diverges as it is a harmonic series. Okay, so you can see that it converges between -2 and 2 and also converges at -2, okay, but diverge at 2. Okay, so let's put down this conclusion here. So what do we get? So the series converges on -2 and 2, but not including 2. Okay. Okay, so let you, is it okay? This example here. Okay, so let you try this example. Try use ratio test, and then see what x this series converges. Would you try for 3 minutes? Okay, so when the question asks you for x, right? Okay, you have a condition from your ratio test, and then using that condition, you can find a condition on your x. Okay, you can see that these questions, right, reduce the question of series to sequence and limit. Okay, so that's why you learn sequence. What, what do you get? What do you get? What do you get? Does everyone get this limit here? What's this limit here? What's that limit? Does everyone got this limit here? This limit is 0. Okay, 0 times any number is less than 1. Okay, so this means whatever my x, whatever my x put here, okay, then it is always less than 1. Okay, so it is true for all x. Okay, it is true for all x. So what does this mean? This means that the series converges for all x. In other words, we say converges everywhere. Yeah, everywhere it converge. Okay. How about the next one? Try and compute n factorial times x to the power n. So what's this limit here? To make sure this is less than 1. Does everyone got this limit here? N plus 1, okay? So what happened to n plus 1? Huh? Diverge. Okay, so diverge. So what x can make this thing less than 1? 0. Okay, if we pick x to be 0, then the whole term inside is just 0. So limit n to infinity is still 0. Okay, so we are not talking about 0 times infinity here. We just 0 multiply n plus 1. Okay, and then we look at the constant sequence 0. Okay, so since the sequence n plus 1 diverges, it follows that x has to be, the absolute value of x has to be 0, which is only when x equal to 0. Okay, so what are these three situation here? So first we see that the series might converge within a finite interval. Okay. Second, it may be maybe the interval is just the whole real line. Okay. Third, it may be just one point. Okay. So this is our theorem here. So the set on which a power series converges is always an interval. Okay, three types of them. One is the single point. Second is an interval minus r to r, where r is not 0. And we might or not for the both endpoints. The other one is the whole real line. Okay, so the r we find in case 2 is called the radius of convergence. It's radius because it is radius from the origin. Okay, minus r and r. So in the case just now, right? Okay. So what's the radius of this convergence, this series? We find that the series converge for x in between -2 and 2. So what's the radius here? Huh? 2. Okay. So the radius here is 2. So radius of convergence is 2. Okay. Okay. So yeah. So the radius of convergence in each case is 0 for the first point because there's only one point, and then r for interval from minus r to r, and r equals the radius is infinity when it is a whole real line. Okay. So these are the examples of radius of interval of convergence. Either you only converge at one point, a single point 0. Either you are converging on this 4 types of finite interval, or the third situation is you converge infinitely everywhere. Okay. Next is the more general form of this series is Cm times x minus a to the power n. Okay. Where this power series is centered at A. So whenever we talk about power series, right, usually we assume that it is centered at the origin. Okay. If it is centered at A, you add a x minus f factor in. Okay. So in this case, we can reformulate the theorem here. Okay. It's really the same, but we just centered it at A instead of 0. Okay. Okay, so one thing to note here is how you usually get the radius of convergence. Okay. How you get the radius of convergence? You just take Cn plus 1 over Cm, and then you get the number out. So let's take an example just now. So let's repeat our example just now. So let's see this example here. So how we obtain 2 actually? Okay, let's go back to our previous example and then see how we obtain the 2. Okay. So what is Cn is this case in this case? Okay. So Cn, we just care about the term that the coefficient of our xn. So realize that when we do computation just now, right, the s just there as a modulus, and then we move all the constant to the other side. So this is what precisely we are doing here. Okay. So let's look at the limit of n infinity of Cn plus 1 over Cn. Okay. Let's see what does this value give us. Is this 2 or 1 over 2? Right. So what's this here? So what we left with is n plus 1 over n plus 2, 1. Okay. So this limit to just 1 over 2. Is it right? So 1, I rewrite this here. So we really can throw away this modulus because everything inside is just positive. So if we multiply 1 over n to the first fraction, what we will get is just 1 times half, which is half. Okay. And then the radius of convergence is 1 over L, which is 1 over 1 over 2, which is okay. So the radius is convergence is 2. Mesh up, right? So why is it 1 over L? Right. Remember that just now we want to make sure this number is less than 1. And then we move the constant to the other side. Right. Okay. This is the formula, but I think you should see why it is true from our computation. Okay. It's not hard to see, but you need to compare the two computation there. Okay. All right. Questions? Any question? Any question? Any question? Yeah. So I mean, listen to what people say is really important skill, right? Okay. I know that maybe you can ignore what I said and go back and study using a textbook, but I want to tell you that, for example, in my research, right? So when you go into the frontier, right, there's no more books for you. There's no more textbook for you. Textbook is not even written yet. Okay. So how the knowledge get transmitted is through the person that found the knowledge. So first they use oral. Okay. So you really need to get the skill of listening what people say, and then try to differentiate whether that person, what the person says is correct or wrong. Okay. Of course, I know you can study from the books, but this is another skill you need to learn in the university. Okay. Any question on finding radius of convergence using this method? Okay, let's try a few examples. Okay, let's try a few examples. So try and find the interval of convergence of this series here, and also the radius of convergence. Okay, so what's your AN here? Okay, so the AN here is a big chunk of fraction, which is minus 3 to the power n, x to the power n, over square root of n plus 1. Okay, so you need to make sure that the ratio of AN plus 1 over AN of the absolute value is less than 1. Let you try first what simplified version, fraction you get. You want to make sure that this huge thing is less than 1. Here, observe that the Sn plus 1 over Sn term always reduce to x. Right? Okay. Because this is the power series. When you compare, you definitely compare the Sn plus 1 term over Xn. Okay. So you always get this cancellation. But what is special? What is different for different power series is the coefficient. Okay. So the coefficient is really the part that testing you whether you know the limit of sequence or not. Okay. So what's the simplified fraction you get here? You get square root n plus 1 over n plus 2 times 3 absolute value of x. Does everyone get this? Okay, good. Okay, so what's next? What's that sequence converge to? What's the sequence converge to? Huh? What does this sequence converge to? How to compute the sequence? Okay, so square root x is a continuous function, and then n plus 1 over n plus 2 also continuous. So you can bring the limit in. So what do you get? You just get square root 1. Yeah, square root 1 times 3, you get 3. Okay, so what you get is 3 times x. So here I should say this one is equals to square root. Huh? Can skip. I'm not sure you guys understand or not. Does everyone understand? If everyone understand, then I skip. Should I write down? Huh? Exam no need to write. Exam. I don't think so. Don't need. Yeah. But when you are specifically asked about this question here, right? Then you need to write. Yeah. If just this question here, then you need to write. Okay. So this you can bring the limit in because okay, just to make it full, I just write out as square root is continuous. Okay. and then so on. For example, I think in your tutorial question, you have ln of some big function or also, right? So ln is also continuous, so you can bring the limit in. Yeah, or the exponential or so on. But of course, you need to check that the function inside also continuous at the point. Okay. So what's this here? So this implies that x is less than 1/3. Okay. So what's this? Does anyone recognize what's this here? What's this limit here? In the radius of convergence context. This part is the L we mentioned. Okay. This is the L. See? The limit of Cn plus 1/Cn is L. This is the L. And then the radius is 1/L because we move the L to the other side. 1/L. So that one is the one appearing in the ratio test. Okay. So radius is, what's the radius? So the radius is 1/3. Okay. So within minus 1/3 to 1/3, it converges. Absolutely. Absolutely. Okay. So this is the radius. But the question asks about the interval as well. Okay. So by ratio test, you don't know whether the endpoint converge or not. Why? Because at the endpoint, the limit, the L is equal to 1. Okay, ratio test is inconclusive. So you need to check it manually. Okay, you need to check it manually. So let's look at where it is. What happened at x equals to minus 1/3. Okay, let's see what happened here. So what happened if we substitute x equals to minus 1/3? Okay. So you can see that the -3 cancel, right? Simplify. So we just get 1/square root n. So 1/square root n, does this converge or diverge? Converge or diverge? Converge or diverge? 1/square root n plus 1. This converge or diverge? Over square root n plus 1. Is this 1/square root n plus 1 close to any function that you know? 1/square root n, okay? Can you compare these two or not? How? 1/square root n plus 1. Yeah. Okay, so P series. Okay, let us recall what's P series. So what's P series? Okay, so P series says that the series of 1/n to the power p converges if and only if p is greater than, strictly greater than 1. Okay, so how far is this from P series? Okay, 1/square root n. So how can you compare? Okay, so okay, let's see what we know. Okay, so the series of 1/square root n converge or diverge? Diverge, right? Okay, due to P series diverges as P is less than half. Okay, equals to half. equals to half, which is less than 1. So this diverges. So what can you tell about 1 over square root n plus 1 in this case? Okay, so smaller. Which one is bigger? Which one is smaller? Which one is bigger? Which one is smaller? What? What's correct?
This one's correct. One square is larger. One square is larger than 1 over square root n plus
1 over, you mean this one? But 1 over square root n diverges, right? So if the big one diverges, can't determine, right? Yeah, cannot determine. So how? One over square root n plus 1.
1 over. Use comparison.
Oh, let's try. So 1 over square root n plus 1 is greater than 1 over n. Okay, so this one, this diverges. No, nothing. Lagi? Okay, why? Lagi Okay, let me start again. Okay, so another try is this one, second try. So let's try second try. Is this true? Okay, so if this inequality is true, then because we know the Hamilton series diverges. But is this true? So this is true if and only if n is greater or equal to square root n plus 1, which is n squared greater or equal to n plus 1. Is this true? So let's try. So n squared minus n minus 1 greater or equal to 0. We factorize this. We not factorize this. Okay. But this is true. This is true when n is strictly greater than or greater or equal to 2. Okay, I think works. Okay, so I think works. So this implies that the sum of n equals to 2 to infinity over square root n plus 1 is divergent by ordinary comparison test to the sum of n equals to 2 over infinity of 1 over n, which diverges due to complete series. Okay, so because the divergence or convergence doesn't affect by a finite terms, so if you add back the finite terms, it still diverge. Right? Okay. So these finite terms doesn't affect convergence. The sum of 1 over square root n plus 1 is divergence. Diverges. Okay. Okay. I think good. I think I got the wrong answer last time for the math student. I need to tell them. Okay. 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 So let's do another endpoint and then we will take a break. So we're at x equals to 1/3. What happened to x equals to 1/3? Okay. So let's see what happened to x equals to 1/3. Is, what is that formula again? So 1 over 3 to the power n of 1/3 of n over square root n plus 1. Okay, what's this? This is the alternating series of 1 over square root n plus 1. Okay, so does this converge or not? Alternating series. So what's the first test you come out in mind? Alternating series test. Okay, so we just try alternating series test. This is the first thing you can do. So do you have Bn greater than Bn plus 1? I think strictly greater for all n. Okay, so is it true that 1 over square root n plus 1 is greater than 1 over square root n plus 2? Okay, so this implies that you have n plus 2 is greater than n plus 1, which is 2 greater than 1. Okay. So how about second? Okay, so do you have a strict inequality here? Is this a strict one? No? Cannot be equal, right? If it's equal, then we will have the case like 1 minus 1, 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 which the limit doesn't exist. Okay, and the second case is the limit of Vn goes to 0. Okay, so I think in this case here, this is relatively easy to see. So you see that 1 over square root n plus 1 is converging to 0. Okay, so by the alternating series test, it converges at x equals to 1/3. Okay, so all together, what do we have? So the series 3 to the power n, sorry, minus 3 to the power n, x to the power n over square root n plus 1 converges, okay, converges for x in between 1/3, sorry, minus 1/3 to 1/3, including the positive 1/3. Okay. So it converges absolutely from minus 1/3 to 1/3 and converges conditionally at 1/3. Sense? Okay. Yeah. Huh? What do you mean by better than ratio test? What do you mean by better than ratio test? So let me write out what I said just now. So converges absolutely for x in between 1/3, minus 1/3 and 1/3, and converges conditionally converges conditionally for x at wanted. Okay. Yeah, so sometimes right, I know that this new definition doesn't click into your mind yet. So it's better that you keep this definition at your side when you listen to what I say, okay? So that you will know what I say. Because sometimes I talk really fast or just relatively fast to what you understand. So try to keep a list of definition beside you. Okay, if you found I'm hard to follow up. Or you can just ask me to repeat the definition again. That's fine. Okay. Yeah. Okay. Any question or not? So this one is determining x, so it's different from the previous. It's a different flavor of stuff. We want to find x where the series converges. Questions? No? Question? No question? Okay, let's take a break until 9:15 and we will come back.哎，
有好像来我们一学这样子，像我是写来conversion from one series to another proof that I'm series like divergence due to one series to one that like all proof that I'm series 是我写出来的平常的。
哦，你讲如果要用 harmonic diver，你要不要再 prove 那个 harmonic diver？不用，因为我们在班上做过了。不用，我们在班上做过了。我以为你什么，等下是什么东西？什么东西？你讲如果我用这句话的话，我要不要 prove 它？还是这句话要不要 prove 它？不用啊，我上次讲嘛。
想要啊！
我上次讲嘛，你问什么？
我是问你一样问题。
你确定？
确定。
还是我听错？
对，我有来说回你个问，来这边要不要 prove 出来？如果有 PC。
出来的意思，我只是说用这个
我问你要不要写那个 step？
这个什么 step 先？我不是这个 step 很长的不？这个 step 不，我们班上 prove 过的东西可以直接用，除非你是被直接问那一个问题啊，班上做过的东西全部可以用啊，除非那个题目是直接问你这句话，你就要不好，你不会说班上我 prove 过了，这样吗？列掉。
哦，你出来的还是没有出来的？
我本来买了拜五来，结果他早列了。
哦，更贵。
但是一个列掉，是啊，哎，没有办法，破台。
没办法。
破台。
这两个也是 harmonic series 吗？是不是？
对，但是没有，我这个写意哦，你不要抄错哦。我没有写意呢，看一下。呀，那个是一个比较小的呀，写意哦，对，不可以随便呀。
这样就逻辑啊，这样就逻辑啊。这对哦。
OK， 好，这样子 OK 啊。没事，我问你老师，就是好像刚刚这个。哦，是的，我不能说。
什么？然后下里。
他去拿的盘车，写错了。
哦，看来我不对这个。
这个是 n 等于 e 就逻辑啊。
全部人抄错了。这个东西跟这个其实我们懂它其实只是多一个 times e 在这里吧，是不是？那为什么我不可以 OK 就是刚刚写的东西，这个我 brings to this one， 我 bring to this one，
也是可以。
如果我直接好像刚刚这样子，
多一个东西我想一下，可以，我觉得可以，可以，我觉得可以。
老师，你把你的那个，你的 n 就是 n 等于 e 啊。
我可以碰到后面
对，
所以我的 n 不是从0开始，是从1开始。
这两个还有两个保护色一样。
对呀，
我用这个。
看一下
谁呀？
我这里这个保护色，
如果这个从1开始的话，你这个就要从
0开始哦。
0开始。
Right, it's okay. It doesn't matter.
是一样哦，现在
是我写错 index 像你刚才那样子吧？我就看到这个东西怪怪的。哦，原来如此，原来是 e，它就等于吧？
就可以了。
啊，
所以如果我换我 index，我也可以算的啊，是这样子。
什么意思？
就是我这个 index，我改一改，就是去我的 series 啊，还是去我的 sequence 啊，我可以拿到一样是类似的东西的，是因为它是移去后面或者移前去，所以我可以用那个
只要我
change in。
我要 explain 嘛，就是我只要确定。他们会一样的那个东西。
对，但是其实你这个情况的话，其实它就是一样的，对不对？因为它从零开始，就是那个的从一开始。
反正你刚就是只是去罢了，
我在哪？我在把这个从
变成刚刚那题啊也可以吧？
哪一题是哪一题？
刚刚你讲的那一题吧？
哪一题？哪一题？这个
是吗？这个
我
们不是 prove 到这个是 conversion 的 dimension 不是？
然后
我把它这个把 n 等于 1，我就拿到1 over square root n，我就可以 prove 到它是 divergent。
对，它其实就是等于啊，
是不是等于是？所以我可以 prove 它是 divergent，然后我不用做这样多东西，是？
没有很多啦，
没有很多，
还可以。
会做的话，我真的很酷啊！
这么要哭，不要哭，先想，不要哭先。先想先，不要哭先。不要哭，一定有办法解。你要想，我们出的题目一定有答案的，这一定是可以解的。你不要哭啊！不要哭！我没有拿 open problem 给你。
但是你拿那个answer scheme 放在我面前，我就不会哭。
这个我也可以。
2个。
你 MA 考验的是，
我操！在讲考卷啊，太久了。
等下我会讲，再讲。它其实shift 一下是那个一模啊？什么？都是 ratio test。只有 ratio test， 除非 root test 哦，只有 root test 跟 ratio test 可以给你这种那个 extra 的那个 inequalities， 但是其他就没有啊。我会给你们看那个 list 我会 show you definition。有，等下我会我做。没有，太多 too much 太多了。应该有吧？啊？太多了的。没有很复杂，反正我们班上做什么就是什么，就是这样啊，没有其他怪怪的，没有刁钻的 trigger 的东西，没有就啊什么 cos square 加 sin square 哈 ，cos square 加 sin square， 不会的话你就要戴一个眼镜。戴眼镜。
我有问题的题哦，它是什么？就是那个主播是他最后就不会再加了，他取消了。然后另外一个盘他就direct，像我整个加起来就是 direct，就是这样一个，就我是在 direct，对。
可是你这样子做的话，你就代表你在 rearrange 它哦。是啊，因为你加的你 odd 的加一边 ，even 的加一边嘛。
最后的话，它还一样。
可是理由不一样哦，理由不一样啊，理由不一样。
而且我还讲不空头。
我跟你讲，等下我跟你讲我怎样做。方舟，纸涛来啊。 等一下，
不要等下了，上次也是忘记，
我没有忘记，我有拿的。
有拿没？上次的那个剪刀，我看哪天的时候还心安，不然我来了听到这个没有算到，
我有
就爽
点啊，我已经记得你了。
我听见你哦，我照顾其他人吗？
要照顾你的朋友啊，
那亲，
要照顾你朋友
我。没有照顾那个退学了，
还有一个，
有来，
还有一个，他有点在你。
不知道。
OK 啊，等下要来，
今天很累，
他一定要来啊。
安娜，我没有8000的啦。
还有一个呢，俊宇哎。路上啊，路上，可以可以。没有。什么？啊？是就是。好，谢谢。来哦，请我吃 K 哦。Okay, hello. Okay, testing. So just now, right? We cannot compare this. Hello. Hello. Let's start.
我没有签 AVD 的，跟股份的来的。
Okay, sorry. So let's start. Just now, this problem here, right? We cannot compare when the n is the same, but what can we do here? Okay, yeah, a magic. So what is this? 1 over square root n plus 1 from 0 to infinity. So you need to be careful just now. Okay, some of you didn't notice that where we start here. Okay, 1 or 0. So in this case, we start from 0. Okay, so what do you get? You really get 1 over square root 1 plus 1 over square root 2 plus 1 over square root 3. Okay, what is this? This is really just 1 over square root n. But the n is starting from 1. Okay, so this one we know, right? This diverges due to E series. Okay, so it is really a divergence of E series. Divergence due to E series. Okay. Yeah. Okay. So in this class, right, we show a few methods to the same question. I don't want you to fix to only one method. Okay. So there's a lot of method you can try. I don't want you to just fix your mind. Okay. Is it okay? Just now this question here. We can rewrite 1 over square root n to 1 over square root n. 1 over square root n plus 1 to 1 over square root n. Yeah. Okay. Hey, by the way, the attendance, right? You have some free point because you 80%, right? About 6 times you can absent without telling me why. Okay. Yeah. Huh? 6 times. 6 times. Yeah.
Last 6
Huh? What? Okay. So for the rest, so I mean, okay. So for the usual one, right? Usual one, you can just tell me. Okay, if you cannot come, if you wait, don't do too excited first. So if you like for example you have diarrhea suddenly, you can just email me. Okay, but you cannot every time diarrhea, right? There must be a problem if every time, right? So if this time diarrhea I put you, if you without OAA, maybe I just put you E or this time, right? So need to be reasonable, right? You just tell me. Okay, let me know what happens. Okay, so if you say today I too tired, I don't come. Okay, don't come. They want put A, count as your 6 time, right? You just tell me what happened to you, but don't disappear. If you disappear, right? If you really disappear, right? Then there will be a problem. Yeah, I have to call police. Okay. 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 So this is my stand on the attendance. Okay. So let's left this as exercise homework. Then we'll continue. Yeah, homework. So what to do here? So what's the first step if you want to find interval of convergence and ratio test? Sorry, radius. So first you use the ratio test. Okay, you compute the limit of an plus 1 over an. Okay, which is less than 1. Okay. And then what's the radius of convergence? Is equals to 1 over L. What is L? L is the limit of Cn. Okay. Okay. So what is Cn? What is Cn? Cn is the coefficient of your Sn. Okay. Coefficient of your Xn. So not that in power series, right? We like to start the series at 0. Okay, but the usual series we like to start at 1. Okay, so you need to be careful where we start. And how to determine the interval of convergence? You need to check the endpoint. Okay, check the endpoint. Check both endpoints. Okay. Yeah. Okay, next. So this is the strategy you need to learn. Next, representations of functions as power series. Okay, so this is the first example we learned from geometric series. Okay, the left-hand side is a closed form of function, 1 over 1 minus x, but the right-hand side is an infinite sum. Okay, so infinite sum doesn't make sense usually. Okay, so when it is equal, it converges. So where it converges for geometry series, we need to make sure the x is in between 1. Okay, let's say you see, look at this closed form here. Okay, if you put x equals to 1, what happened to this fraction? It diverges. It diverges. So, okay, so this closed form somehow tells you there's some condition on your x so that this function makes sense. Yeah. Next, so let's say we know how to express 1 over 1 minus x as a power series. So can you do it for 1 over 1 minus x squared? Okay. So how is these two related? 1 over minus x and 1 over 1 plus x squared. Where's the difference? Okay. In mathematics, right, we like to look for pattern. We like to look for difference. Okay, so what's the difference? What's the similarity and what's the difference here? Okay, the similarity is both of them are fraction. Okay, and then numerator, both of them have 1, but the denominator is different. One is 1 minus x, the other is 1 plus x squared. So how do we relate these two? Okay, what we can do is we can change variable. Okay, change variable. We can write 1 over 1 plus x squared into 1 minus x squared. Okay, so you see this minus x squared as the new x. Okay. Yeah. Okay. So in this case here, because this function is in this form here. Okay. So when you see mathematics, right? When we put x here, usually we can substitute anything here. Okay. In this case, we substitute minus x squared. Okay. So what happened is we can express this equal sign as a infinite series. Okay. But be careful that when we want to express something as a infinite series, what we need to take care. The radius of convergence or the interval of convergence. Okay. So what's the interval of convergence when we want to write down this equality here? The x has to be, okay, sure, you need to use ratio test, but let's say we already computed it. Okay, we already computed, right? We already computed. So let's extract the information here. So what's the interval of convergence? What's the x is less than 1. So our new x is minus x squared now. Okay. So we want to make sure minus x squared is less than 1. Which means what? X squared is in between 1 and minus 1. Which implies what? What is in between minus 1 and 1? No. I mean, can you deduce further from this line? Why? we ah sure, right. That's right. That's right. So if you put square root, then you will get complex number. But that's not how we see this problem here. So how we look at this problem here is I got an x. Okay, I squared it. It is in between minus 1 and 1. So I ask you, what's the x I started with? Okay. So I must also start with x in between minus 1 and 1. Okay, so this is an if and only if. So if I started with x in between minus 1 and 1, you square it, you're still inside the range of minus 1 and 1. If you take a number from x squared, it certainly comes from number that is in between minus 1 and 1. Okay, so we are not just doing arithmetic calculation. You don't get it. You don't get it. You don't get it. You don't get it. So you don't believe what I say. You first understand what I say first, and then see if you believe or not. So what I want to say is, okay, so one direction is easier, right? If we start with minus 1 to 1, okay, the number in here, I squared it, okay, it's definitely in between 0 and 1. In particular, it is in between minus 1 and 1. Hello. Is okay. Yeah, I know. I understand that our class is really early. So if you want to come late, I think it's reasonable. But please don't cut. Please don't not come. Okay. Okay. Up to you. You want to do until that stage. Okay. Okay. So you get the first direction or not, bottom to top. Yeah, from negative to 1. If you square it, you definitely get something in between 0 and 1. Okay, which is in minus 1 to 1. Okay. So the other direction is maybe harder to show, but it's not hard to see. Can draw, cannot draw. Cannot, how to draw? How to draw? No, I mean S square won't drop to minus. I mean this. I mean x won't drop to S square won't drop to negative value. Okay, so that means what? Okay, if x square equals to minus 1, right? There's nothing square to give you minus 1. Actually, the pre-image is empty. So there's not, I mean, you cannot find x that's square to minus. Okay. Huh? Not quite, not quite. What I just want to say is there's nothing that's square to minus 1. Okay. So, what? Which one? Get which one? Get which one? You mean this one? This one? Because if you square everything here, it will go in between this range. So okay, let me draw this in let me draw this. So minus 1 to 1 is here, right? Okay. So when you square it, you get this part here. Okay, 0 to 1. Okay. So this is the pre-image for this 0 to 1. Yeah. That's all. That's all I want to say. Yeah. Get what? Get what? Huh? Cannot get. Cannot get. I mean, s square is just a value here. Yeah, s square is just a value here. Huh? No. I mean, First of all, you need to understand the statement here first, and then why is it true? Yeah, it's what I say. Either you understand or don't understand what I say. Huh? Top to bottom, bottom to top also can. Both can. Because I put this direction here. Okay. Yeah. Okay. If you don't understand, then you can try and remember this. Yeah. Okay. Okay. So this is only true for this for all the x in between -1 and 1. Okay. I think there's not much thing. If you want, you can split further minus alternating of x to the power n. Okay. And then what's the interval here? What's the interval here? Did we check endpoint last time? Did we check endpoint last time? We didn't check endpoint last time. Huh? Okay. So what happened? What happened at the endpoint? So let's check the endpoint for last time. Okay. So the endpoint when x equals to 1, what do we get? This thing diverge. Okay. And x equals to -1, what do you get? You get alternating -1. Also diverge. Okay, this one diverge to infinity. The other, the limit doesn't exist. Okay, so at both endpoint diverge. Yeah, limit doesn't exist. Right, alternating 1 and -1. So the interval of convergence is, yeah, you understand? Okay, so the radius of convergence is just -1 to 1. Okay. Yeah. Guantian just now says C from geometry, right? You can see that there's nothing in between -1 to 0. Can you see it? This graph is not here. So it is empty. Nothing gets sent to -1 to 0. And this is what I want to say. There's nothing gets sent to -1 to 0. Yeah. Okay. No pre-image. Okay. Okay. Wait. Okay, wait. Huh? Which one? Which one? What? Which one? Don't understand. Yeah. Yeah, it turns out that they have the same interval of convergence for 1 plus 1 over 1 plus x squared and 1 over 1 minus x. Turns out that they have the same interval. Huh? Finish what? Finish what? Yeah. So you found the interval of convergence and then you express the function as a sum of power series. Okay. Okay, next example. So we're still playing around with the 1 over 1 minus x. 1 over 1 minus x power series. Okay. So why we look at this 1 over 1 minus x series here? Okay, because this is the most basic power series you can get. You just take 1 plus x squared plus x cubed plus x to the power 4. Okay, this is the simplest sum you can get, because that's why we started with this 1 over 1 minus x. Okay, so how we relate these two then? How we relate 1 over x plus 2 to 1 over 1 minus x? We can write 1 over x plus 2s, 1 over 1 minus sorry. So you need to create the 1 first, right? How you create the 1? How do you create the 1 in the denominator? Huh? Huh? We can divide 2. We can divide 2, where you get x over 2 plus 1. Okay. And then we can add the extra minus. Okay. Okay. And then now, what is this? This is a half time a fraction 1 over 1 minus x, where this new x here is minus x over 2. So this is half time the sum from 0 to infinity of minus x over 2 to the power 10. Okay, so again, you write something closed form in terms of infinite series. So what's the condition? You need to make sure it is within the radius of convergence. Okay, so what's the radius of convergence here? You need to make sure your new x is in between n minus 1. Okay, which implies what? This x is in between -2 and 2. Okay. Yeah. So if you want to rewrite the series, you can write it as minus x to the power n over 2 to the n plus 1. So what's the interval rate convergence? It is just from -2 to 2, not including the box endpoint. Okay, because the original equality also don't include the 2 endpoint. Yeah. And then what's the radius of convergence here? What's the radius of convergence? Huh? Okay, radius of convergence is okay. So this means that if my x is in between -2 and 2, these two this power series is equal to the function itself. Later we'll see how to picture this infinite sum. Okay. Later we'll see what's the meaning of this, the geometric meaning. Okay, let's do one more. So again, how we associate these to 1 over 1 minus x. What we learned? We learned 1 over x squared plus 2 already, right? So we can relate to the previous question. So how do we relate? We already found power series for 1 over x plus 2, right? Okay, so what can we do here? What's this? What's the power series representation for s cubed over x plus 2? So when the question asks about power series, right, it is a power series centered at where? At the origin. Okay. So what's this here? So this function here is x cubed times 1 over x plus 2. Okay. But we know how to express x plus 2 already. 1 over x plus 2. Okay, which is what we found just now. It is just the infinite series of minus x to the power n over 2n plus 1. Okay. So what's this interval of convergence here? X has to be in between minus 2 and 2. Okay? Okay. So whenever you write down the closed form equals to an infinite series, you need to measure where this radius of convergence lies. Okay? Otherwise, it doesn't make sense. If you put different x, they might not be equal. Okay. So what's this? This is just the alternating series of x to the power n plus 3 over 2 to the power n plus 1. So where's the interval of convergence? So the interval of convergence is still minus 2 to 2. Okay. Is that okay? Whole series. Okay. Huh? Explain what? Which this question? Okay. So we want to find a power series of representation of s cubed over x plus 2. So power series means you need to write this function as a sum of infinite terms of linear combination of monomials, right? Okay, so you need to make full use of what you have computed before. For example, 1 over 1 minus x, we know how to express it in terms of power series. So we need to make full use of this, okay? So in this question here, what we also know is we know how to express 1 over x plus 2 in terms of power series. So we need to make full use of the previous example as well. Okay, so how we relate to this example here? Notice that s cubed over x plus 2 is just x cubed times 1 over x plus 2. Okay, but 1 over x plus 2 we know how to express in terms of power series. Okay, so this will help us to express the s cubed over x plus 2 in terms of power series. Does it make sense? Yeah. Yeah. How was it? Say again. Yeah, if you what? Okay. Wait. So how was it? Yeah. I mean, yeah. Yeah. Question. Uh-huh. Is the last line necessary? Huh? I would say I think it's better you know. It's better you know. I mean, usually they come in a package. Usually they come in a package. So you will need to know. If it's good, if you can write it down. Yeah. Usually it comes in a package. Once you know the power series representation, you surely know what's the interval of convergence. Oh, you mean this one? You mean this one? Uh, is this necessary? I think this is a similar. I think it's necessary. Okay, this is like you simplify the fraction, so you combine the like term. You combine the like term. It's better you do this. Careful, ma. Get the. Yeah, that's right. The last step is just simplify. It's better. Okay. Hey, Guan Tian, what's your question? Can you ask more specific question? More specific question. Do you know what it means by founding the power series representation or not? Don't really understand. Okay. So then we have to go back. What is power series? Okay. No, I mean, no. I'm showing you how to like read this max statement, right? So if you don't understand what is the power series representation, you need to go back to the word what is power series. Okay. So what's power series? So power series in X is a series of the following form. What's this form here? This form is a linear combination of different monomials in X. Okay. Or in other words, it's a linear combination of power of X. Okay. This sentence you understand or not? Linear combination of power of X. This linear combination of power of X got a lot of things inside there. Means what? You need to multiply each monomial with scalar, different scalar I consider, and I add them up. You get what I mean? So inside a single terms, right? There's a lot of operation here. You need to imagine. Okay, when I say take linear combination of things, so you need to consider scalar multiple of them, and then I add them up. Okay. Right? Cannot imagine? Cannot imagine? Cannot imagine? Okay. Let's. This is a really convenient word. Okay, this is a linear. Okay. The problem. That's the problem. Okay. So let me explain this word. This word is very convenient. Okay. Let's say I say linear combination of these two things, right? It means what? There is A inside there, plus B inside there, A minus B inside there, 0 also inside there. So you can take any scalar of them and then you add them up. Okay. So you may think, why I get 0? Okay. Because I can take 0 times A plus 0 times B. 0 is a scalar. Okay. So everything here I can write as, for example, A I can write as 1 times A plus 0 times B. Okay, this is linear combination of these things. Okay, so similarly, we have this, right? Linear combination of monomials in X. Make sense? You can put any scalar in front and then add them up. Linear combination. Okay. Any. Any. Who is any? Okay, so just now we look for a power series representation. So just now, that function is, for example, 1 over 1 minus x, right? This is not a sum of, not a linear combination of power of x, right? Isn't it? This is not right. Okay, so you need to find a representation to represent this. Okay, but how do we find for 1 over 1 minus x? So how we figure out the infinite sum? Who still remember? How we figure out this infinite sum here? We use the fact that we know about the geometric series. Okay, how geometric series converge, and then that converge give me a formula. Okay, to find 1 over 1 minus. This is a bridge for us to go to power series. This is the bridge. for now. Okay. So this is the bridge from 1 plus x squared and so on. Maybe write this one. Yeah, this is the bridge. Okay. This is sum of infinity. Sum to infinity. Sorry. Sum to infinity. Okay. So how we build this power series and this 1 over 1 minus x is through the sum to infinity bridge. I think historically is right to left. Right to left. And then later we will see how to go from left to right, which is called the Taylor series. Later we'll see. Okay, how to go from left to right. Okay, so when we want to find power series of representation, we need to express our function in terms of linear combination of values in x. Okay, or the power of x. Okay, n power of x. Okay, okay or not? Okay, hello, hello. Okay, why the question don't need to consider the x cube? Oh, you mean go back to the question, huh? Okay, so what happens here? So you can see that this is obviously not a power series representation, right? Because beside x cube, what do you have? You have 1 over x plus 2. It's not a scalar. Okay, you need to write in terms of an infinite series of scalar multiplied by power of x, right? Okay, but you can see that this s cube here doesn't do much to our infinite series as long as we can, because s cube is already in the power of x. Okay, those that are not in the power of x is 1 over x plus 2. If we can express 1 over x plus 2 in terms of infinite series of power of x, then we just multiply s cube to all of them. Then it becomes another infinite series in terms of power of x. You get what I mean? Okay, again. Let me bring down this what's power series. So what's power series? It is in the form of power of n with a coefficient scalar coefficient. Okay, so how far is this function from this function? Okay, how far? We already have s cubed, right? Power of x, we already have it. But beside s cubed, what we have? X 1 over x plus 2 is not a scalar, right? 1 over x plus 2 is not a scalar. Okay, so how do we express 1 over x plus 2 in terms of power of x? Okay, we need to use the bridge, the only bridge we know for now, which is the sum to infinity. So we need to link it back to 1 over 1 minus x. Only from there we can express 1 over 1 minus x in terms of power series. Okay, does it make sense? Make sense or not? Okay. Okay, you just see question. I see some confused face. A lot, huh? Still confused? Huh? Better? Much better? How about I ask one guy? Daniel? Do you understand what I say? Huh? What? Sorry? A little bit. A little bit. What you don't understand? No, just now I asked from you, right? So let's ask from others. What you don't understand? Or you don't know why we did this? Why we do this? Oh, that question I cannot understand. Cannot answer. You have to answer. Huh? Okay. Listen. Huh? You still do you know what the power series is? What's the power series? Power series is okay, use the name to remember. What's the power series? Power series, first of all, is a series. Okay. What's power? Power of x. Okay, power of x. Okay, linear combination of n power of x. Okay, series. So series, you need to tell me what sequence you want to add up, right? It is a sequence of n power of x with different scalar. Okay, can understand? So this series here, yeah. So this series here is a series of n power of x. Okay, with different scalar. What's the series for this? You mean this example? Here, this one. So I write it down. Let me write down. Okay, let me write down. So first term is 1 over 2 x to 3 plus what? 2 is 1 minus 1 minus 1 of 2 to the 2, which is 4, x to the power 4, and then plus 1 over 2 to the power 3, which is 8, which is x to the 5, and then so on. Okay, maybe you see that, just now you said that power of x, right? We still got one constant term, linear term, quadratic term. Where are those? Because we can just take C0, C1, and C2 to be 0. Okay, we just take C, so we just add 0 times 1 plus 0 times x times 0 times x2. And then you can compare, are these linear combination of n power of x? Yes, because C0 is 0, C1 is 0, C2 is 0, C3 is 1 over 2, C4 is minus 1 over 4, and then so on. Right? So this is a power series as a representation for this function here. Okay or not? Okay. Okay. So you need to go back to the word power series. What is power series? What is power series? Okay, what is power series? Okay. And then what's the tool we use here? It's the sum to infinity. Okay, this is the only bridge we know for now. Okay. Soon we will introduce another bridge. Okay. 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 So express a function in terms of power series, linear combination of n power of x. Okay. You blur? What? Yes. You blur. Anything you want to ask, or you can you want to settle yourself? Okay. You settle with me later. Okay, next. Okay, next. So we have this infinite series, right? We want to differentiate. Okay, we want to differentiate them. We can differentiate term by term as long as it is within the interval. Okay, we can differentiate because, for example, we can differentiate. Do you know how to differentiate 1 over 1 minus x? Okay. You use the chain rule, right? Chain rule. Use the chain rule. So you get minus 1 over 1 minus x squared, I think. Okay. But on the other hand, you also know that 1 over x is equal to the sum of 1x, x squared, and so on. Okay. So since they are equal on the radius of convergence, can I also differentiate the right hand side? Okay. So how do? You just differentiate 1 by 1. Okay. Only within the radius of convergence. Okay, only within the radius of convergence. Similarly, if you want to integrate the left hand side, you also can integrate the right hand side term by term. Okay, because right hand side should be easier, right? Because it's just polynomial. Okay, you just play around with the power of polynomial. So let's try one example. So determine the radius of convergence and then find an explicit formula for this series when it converges. Okay. So one direct way you can use is what? What's the strategy we say just now? If you want to find the interval of convergence. Use the what? Very random. I found homing very random one. So how to find radius convergence for a series? What test? What test? Ratio test. Okay. So one method is you can use ratio test. Okay. This one you try yourself. I show you one advanced method now. Use ratio test to try out. Okay, so now we use the advanced method and what we have learned. Okay, just now the theorem is not for fun one. Okay, so we want to use it. So what is 1 plus 2x plus 3x squared plus 4x cubed? Okay, you can see that the number, right, there's some pattern here. Okay, 1, 2, 3. And then the power of x is also 1, 2, 3. Okay, but in a slightly off order. Okay, what is this off order doing? This is really the differentiation of the series x plus x squared plus x cubed plus okay. And it doesn't affect that you add another constant to the series, right? Because you differentiate a constant, you get 0. And what is 1 plus x squared plus x cubed? Okay, what's this? This is the, use the bridge. What's the bridge? It's the sum of sum to infinity here. Okay, using the geometric series. So when you establish this bridge here, there's a radius of convergence. What's the radius of convergence? X has to be in between 1 and minus 1. Okay, so now you can differentiate the 1 over 1 minus x. So what's that? We already do it just now. This is just minus 1 over 1 minus x with the radius of 1. Radius of convergence is 1. Convergence is 1. Okay. And then what we have found here? We have found here this power series representation is for the function minus 1 over 1 minus x squared. Okay. Yeah. Why can we differentiate term by term? Because we do it in the radius of convergence. Okay. We do it within the radius of convergence. Okay. Yeah. Otherwise, the differentiation, you need to go through the limit definition. Okay, but we don't. So we pass by the limit definition. And then we have this theorem here. Is it okay? Question. Hello. Hey, discuss with me. Discuss with me. Huh? Don't have the formula. Can you deduce a formula? I think you can, right? This is what? I think you can deduce a formula for this guy, right? So this is a sum of n. So let's start from n equals 0 to the power n plus 1 over, not over. I think this is the formula, n plus 1 times xn, right? Then you can use ratio test. Okay, you can check that you use ratio test and this method also they give the same radius of convergence. Okay. What? Right. Hey, sometimes right, sometimes you need to believe me first and then you go back and check it. Okay. You cannot expect me to do everything here, right? No time. So sometimes you need to accept first, then you go back and check. If it's wrong, then you come back and talk to me and then fix it. Huh? Second line and the third line. Where's the second and the third? This one. Second and the third. This one. This one and this one. Second and the, sorry. So second and the third. Yeah, so the difference is I add a 1, right? Yeah, differentiate constant, you also get 0. Okay, what's the difference between these two? I add a 1 here. The differentiate constant, what do you get? Why I need this, right? Because I know the power series expansion here, representation here is just 1 over 1 minus x. Ah. Oh, I know what's going on now. Okay. Okay, I should spend more time explaining question first. So, okay, this question says that you want to find the radius of convergence of this power series and then find an explicit formula. So you want to find a closed form of this function. Okay? Yeah. Closed form. I call it a closed form because it's closed, right? 1 over 1 minus x. It's not like infinitely many terms. Oh, no. I'm just dealing with him. So it's okay. Okay. So I mean yeah. So I'll call this 1 minus 1 over 1 minus x as a closed form because it's close. Because I mean so how to say closed form. I don't want to go into the definition. I mean, huh? What? What do you mean? Wait, do one by one first. So, okay. So when I say closed form, right? I want to say it is in term of a fractional function. I think yeah. For now, I take it for the definition. Okay. Yeah. Asia. And you need to talk to me because I really don't know, like sometimes your language. So I need to know your language and then I can go through your language. Huh? How do you know the close is? Okay. So yeah, so I know. I mean, this question is not as precise, but when they talk about this explicit formula, right, you want to relate back to some function that you know, some continuous function that you know. Yeah. Yeah, yeah, correct. Okay. Correct, yeah, right. So I mean, okay, when we talk about this explicit formula, right? We are looking for some continuous function. Yeah, continuous function. Continuous function. Yeah, continuous function that you know. Okay. Yeah. No. No, that's not implicit here. This explicit here. Right. So how to explain this? This is just terminology, huh? Wait. Why? Can rule, right? Oh, minus become positive, huh? Okay, yeah, right. You go the minus from the power and then you go the minus from the channel. Yeah, explicit formula, I mean, okay, so first of all, think of it, what we have learned. So we learned that we can express a continuous function as a power series. So now given a power series, they want you to find a explicit formula, right? Okay, so from first sight, you will think that it's just the continuous function. Okay. and give you a continuous function that asks you for a power series representation. So you go from left to right, right to left, like this. This question is just like this. Okay. Don't yeah, okay. Yeah. Don't say much. Okay. Okay, I will spend more time talk about question first because sometimes don't understand the question. So okay. So now you can see that next example, we have this power series. Is this a power series, first of all? Yes, right. Okay, because it's x squared, s cubed, s4. But what's the constant term here? 0, good. Okay. And then now we want to determine the interval of convergence and then also find an explicit formula for this series. So if you really want to think about an analogy of explicit formula, right? So you can think of the explicit formula for the series, for the geometric series, okay? Which is the sum to infinity, okay? So this is the analogy you need to think about, okay? Can follow now? Can I? Okay, better now. Okay, so determine the interval of convergence here. So what's the first thing you can do? You can use the what? What's the 以信啊？以顺还是以信啊？以顺 yeah. What do you say? Huh? You want differentiate, okay? Differentiate what? What? What do you want to differentiate? Okay, so I mean, the very first thing you can try is still the ratio test. Okay, if you like. Okay, but now we will use a different method. You want to differentiate? Differentiate what? Do you get this formula here? Or you want to differentiate the whole thing? You want to differentiate the whole thing? Okay, let's see what you observe, right? Okay. Okay, sometimes I don't want to straight away tell you what to do because I don't want to limit your imagination. Right. So let's say you have this observation here, right? Is this what you want to do? Differentiate this guy. Because if you differentiate this guy, what you see? If you just see the geometric series, right? Okay. In another word, this is what we can express the original function. This is let me put it here first. Okay. In other words, we have what? This term here is equals to the sorry. Let me write it. X squared. Hey, what time we finish class? 11. I cannot finish, so I think. Okay. So this is equal to what? From 0 to x of 1 plus t squared plus t cubed, and then up to dt. Right? Okay. By this one. Okay. So what's next? We know that the sum of polynomial is just the what? The sum to infinity of geometric series. So here we introduce in the radius of convergence, right? When we write the infinite series in terms of explicit formula or closed form, this is where we introduce the radius of convergence. And then from here, what do we get? From here, what do we get? Now what do we get? Minus ln of 1 minus t from 0 to x. Okay, so what's this here? This is just minus ln of 1 minus x. Okay. So what's the radius of convergence here? So what's the radius of convergence here? Okay, so what's the radius of convergence here? What's the radius of convergence here? Is equal to 1. Okay. So it converges for x in between -1 and 2. Since this is a new power series, right? You can also check at the endpoint what happened. Okay. Sometimes will give you a surprise. Give you a surprise. So if x equals to 1, right? Okay, what do we get in this case? Then we get 1 plus 1/2 plus 1/3 plus 1/4, which is divergent. Okay, which is divergent, as it is a harmonic series. If x is equals to -1, then we get the alternating harmonic series. Which converges. Okay. Okay. Not that we are just integrating or differentiating within the radius of convergence. We are not doing at the interval. Okay, we only do it within the radius. So at the interval, you still can check. At the endpoint, you still can check whether the series converge at the endpoint. Make sense? Does it make sense? Does it make sense? Okay. Question? Okay. Okay. So integration and differentiation, right? Only works within the radius of convergence. Okay. And then you still need to check the endpoint whether it converges or not. Okay. So this theorem here, see this theorem here. This theorems here only work inside the radius of convergence. Okay, you can see that they don't include the endpoint here. So at the endpoint there, you still need to check. So this is true inside the radius of convergence. Okay, don't including the endpoint. So these endpoint stuff, you need to be careful. Okay, 10, 18. So let me think. What should we do next? Let's try one more. Okay, let's try one more. Find the power series representation for ln 1 plus x. So you can see that see this question, they give you a explicit formula and then they ask you to find the power series. And then if they give you a power series, they ask you to find the explicit formula. Okay. So this question says find the power series representation for ln 1 plus x. So is ln 1 plus x already a power series or not? Is ln 1 plus x already a power series? Oh, I mean for just ln 1 plus x is not, right? Okay. So and determine its radius of convergence. Okay. So this is not in terms of power of x yet. Okay, but Ming says that we already learned something else. Right? We learned something else. What do we learn? We learn how to relate the minus long than this. Okay, so we have this connection here. Okay, we have this connection here. Okay, we have this connection. Okay, so yes, we have this connection here. Okay, we have this connection here. Yes, that's right. We have this connection here. Okay, what's this? But we want 1 plus x, right? Okay, 1 plus x. So what do we do? What can we do is we can do a change of variable, and then we'll see that this equality is true. If you don't believe me, you just integrate this 1 over 1 plus t. Also fine. Okay. So the idea here is we only know one bridge, which is 1 over 1 minus t. So we need to always relate back to 1 over 1 minus t. Okay. So how to relate back to 1 over 1 minus t? We can write 1 over 1 plus t as 1 minus t. This is what we did in the previous question. So from here, we can go to the power series expansion, okay, or representation. But it is true only within the radius of convergence. Okay, here we need to introduce the radius of convergence. But the theorem says that within the radius of convergence, we can integrate the power series term by term. Okay, integrate power series term by term. So how do we integrate this? So what's the formula for this? It is just minus 1 to the power n, t to the n plus 1 over n plus 1, which is from 0 to x. Okay. Yeah. Which one? The previous two? You mean this one, huh? This one, huh? This one. Okay. So, okay. So how you integrate minus t to the power n? Okay. Over with respect to t, right? So you need to bring the power, increase the power, and then divide by n plus 1, right? Integrate the increase, yeah. Okay. But minus 1 to the power n is just a constant, right? So you bring it up. Okay. And then you evaluate from x to 0 to x. So when x t equals 0, you just get a 0 term here. So what you left with is when you substitute the x. I go split the negative one because negative 1 is a constant. Okay, and then this negative 1 depend on what n. Right? Yeah. Negative 1 is a constant. Okay. Okay. So what's the radius of convergence here? 1. Okay, radius of convergence. How about endpoint? How about the interval? Equals to 1. So you can try and check that actually the interval is, try and check the interval of convergence is minus 1 to 1, including 1, including positive 1. Okay. If not, you can straight away see here. Okay, you can just straight away see here. Okay. You also can straight away see here if you like. -1, you will get a harmonic series. 1, you will get a alternating harmonic series. If not, you can check. Okay. Okay. Question on this example. There's a question on this example. Okay. 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 Next question, right? I only tell you. So let's say we want to find a power series for tangent inverse of x. Okay. So tangent inverse of x is not a power series yet, right? Okay. You want to relate it back to 1 over 1 minus x again. Okay. So there's one useful identity you can use is test tangent inverse of x is just the integration of 1 plus t squared dt. Okay. And then you can try work it out from here. If you I'll provide you solution later. Okay. This one I leave it for you to compute first. Next one is to find a formula for the sum of the series. So you are given a power series. Now you want to find a formula for it. Okay. This one I also let you try first. I will provide solution also. This question a bit tricky. This question is a bit tricky. Hey, how about do this? This one is a bit fun. Okay, do this. This is a bit fun. Let's do this. Huh? Yeah. I mean, not this question, this particular question. Okay, not this particular question. Okay. So what's this? So how to find this sum here? Okay, I think you don't copy first. You just listen to me. Don't copy this question. Okay, because this question is not it's not usual. Okay, just listen to what I said. Don't copy. Don't copy. Stop your pen. You just listen as a story. Okay. So find a formula for the sum of the series. Okay. So for first thing you can do is use ratio test and see what's the radius of convergence of this series. Okay. So what's this formula here? Okay, let's write down a formula for this constant. So this is n equals to 1 to infinity of x to the power n over n factorial. Okay, this is the formula for it. So if you use the ratio test, right? Okay, we want to find what is L. Okay, what is Cn plus 1 over Cn? Don't copy, listen to what I say. So what is Cn plus 1 over Cn? 1 over n plus 1 factorial over 1 over n factorial. N, what do you mean by n? Oh, yeah, okay, good, thank you. Okay, so what's L here? The L here is 1 over n plus 1, which is 0. What's the radius of convergence here? 1 over L, which is infinity. Okay, but we want to find what's the explicit formula of fx, xx, right? Xx. So how to find? Okay. So a little bit tricky here. So what you can observe here is, let's say if we differentiate this infinite series again, what do you get? You get 0 for the first term, and then 1, and then x, and then x squared over 2 factorial plus s cubed over 3 factorial, and then so on. What do you see? You see the same xx. Okay. Okay, so what is this here? So this says that you differentiate your series x to xx is equals to xx again. Okay. So you guys haven't learned ODE. Have you guys learned ODE yet? Or the ordinary differential equation? Not yet. See before? Roughly see before. Okay, roughly see before. So in the ODE, right? If you want to solve for ODE, you need to have initial condition. Okay, initial condition. So initial condition is here is x evaluated at 0 is 1. Okay, you start from here. Okay, so we have like d of this thing is equal to x sub. Okay, we want to solve this. So how to solve this? So you haven't learned ODE, you haven't learned separation of variable, right? Okay, never mind. Everything you never learn, never mind. What to do? Okay. Let me see how to present to you if you haven't learned anything yet. So so what we have here is you have let y equals to xx. Okay, what do we have? We have dy dx equals to y. Okay, so what we can do is do I want to show you this magic? Show you magic. Okay, let's show you this magic here. Okay, this is called the separation variable. I think the last chapter in this course is ODE. Later, I think you will see again. Okay, so what's this magic here? This magic here is we can what? We can what can we do? So we can move all the y to one side and then move all the x to the other side, and then what we get is ln y equals to x plus. Okay, why we got ln here? Because we got a 1 over y here. Okay, there's some magic called separation of variable. You can do this. And then what else? What's the next thing? Okay, this is the really interesting things coming soon. Okay, what's this? This is just e xx is equal to e to the x plus e. Okay, so this is the magic here. Okay, okay, this is the magic here. So what's this? What's this here? Because ex is always positive, right? I can really throw away the modulus. Okay, and then what's the constant here? This constant here is determined by our initial condition. Okay, so this implies that a has to be equals to 1, right? Because if you sub x equals 0, you get e to 0, which is 1. 1 a equals to 1, a is 1. Okay, so this implies that xx is equal to e to the power x. Okay, so this is the second bridge. Okay, not the second bridge. This is the this is the another bridge you learn. Okay, so ex is equal to the sum of power of n, but the coefficient is 1 over n factorial. Okay, this is the second power series you learn. Okay. Yes, this is the second formula you learn. Okay. e to the power x is equal to the power series of n power of x with the coefficient 1 over n factorial. Okay. And then this is the one I used to show. Hey, hello. This is the one I used to show 1 over the integral of 1 over ln t diverge. Use this one. Use this power series here. Yeah. Because after you do the variable change, you become e to the power t over t. And then you use this. Okay. Yeah, last time I used. Maybe, probably, yeah. 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 Probably, yeah. Okay. Haven't finished, huh? I want to continue. So just now we only know what do we know? We use sum to infinity first, or for 1 over 1 minus x, we use sum to infinity to find, right? And then this one we use ODE method to find. Okay, so what are these? So these are actually not something out of the blue. Okay, actually there's something behind this equality here. Okay, which we call the Taylor series or the Maclaurin series. Okay, so what are these coefficients really? So what are these coefficients? So this coefficient is really the n derivative of our function. Okay, so for example, C0, what is C0? Okay, so C0 is, so what's the constant? So the constant is the function evaluated at the point that we expect it. Okay. And then what is C1? What is the coefficient in front of x? It is the first derivative of our function evaluated at the point we expand. Okay. So this one is let's say, yeah, let's put A here because we start with A, centered at A, and factorial, which is f prime A. And then what is C2? Okay, C2 is the second derivative of our function divided by 2 factorial, which is 1 over 2 factorial of f prime. Okay, so in this way, right, you can quickly recover what is the power series expansion of EX at x equal to 0. Okay, let's write down power. So example. So let me write out. So example, power series of EX centered at x equal to 0. Okay. If you haven't yet finished looking at the definition, don't worry, just listen to what I say. So what I say is the coefficient of the power series is the n derivative of our function. Okay, so let's say we have this EX here. Okay, we have this EX here. What is the power series expansion? Okay, what's the power series expansion? Just now we say that we want to write it as C0 plus C1x plus C2x squared plus C3x cubed and so on, right? Okay, so how to get this C0, C1, C2, C3? How do we get this? N derivative of our function evaluated at the point it's centered at. Okay, so what is C0? Okay, C0 is x equal function evaluated at x equals 0. Okay, what is C1? Okay, C1 is differentiate our functions once evaluated at x equals 0. Okay, and then x. Okay, and then there's always mistake here is remember to put in the factorial. Put in the factorial. Okay, later we'll put in the factorial. So what is C2? Okay, C2 is the second derivative of our function, okay, evaluated at s equals 0 divided by 2 factorial, okay, times x squared. And then what's the third one? Differentiate our function 3 times evaluated at s equals 0 divided by 3 factorial x cubed. And then so on, okay? So what's the derivative of EX? X. no matter how many times you still get EX, right? So for n of them, there's still EX. And then evaluated at x equals 0, what do you get? You just get 1. Okay. So what do you get here? You get 1 plus 1 times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus 4 factorial times x squared and so on. Okay. So this is how we recover the power series of EX using the Taylor series. Okay. When it is centered at x equals 0, it is called a Maclaurin series. Okay. Taylor series is centered at any point. Okay. Maclaurin series centered at x equals 0. Okay. Taylor. So I write down. So Taylor series is let me write it down. Yeah. So Taylor series is a power series at centered at any x if x is equal to 0, then the Taylor series is also known as a Maclaurin series. This is just a terminology. Is also known as Maclaurin series. Okay, it's also known as Maclaurin series. So let me start. Okay. So note that there's extra factorial stuff here, right? So you need to remember that when you find the n derivative, remember to divide by the right n factorials. Okay. You can see that if you don't divide by 2 factorial, 3 factorial, 4 factorial, right, you won't get the right power expansion for EX. This is how you remember. Okay. How you remember, you can remember from finding the Taylor series for EX, e to the power x. Okay. Remember the e to the power x, you have 1 over n factorial for all the coefficient of power of n. Okay. Is that okay? So remember this example, then you will remember how to do for the other examples. Okay. How about we do one exercise? Let's do one exercise here. Wait. So this example are quite limited. So let's try another example, right? So let's try. Okay, let's try. I cook up example from what we do just now. So find Taylor series of 1 over 1 minus x. Okay, let's try this. Find Taylor series of 1 over 1 minus x centered at x equals to a. Okay. So by the formula, what's the formula of Taylor series? Okay. So let's recall what's the formula. This is equal to the sum from n equals 0 to infinity of what? Of the derivative, the n derivative of, okay, let's put fx first. The n derivative of f, evaluated at a divided by n factorial of x to the power n. Okay. If you don't remember the statement just now, right, it's okay. You just follow what I say now. Okay, later you can go back and revise again. Just remember what I say now. Okay. So let's say we have this formula here. Okay. So we need to work out all the coefficient, right? Let's say now our f is 1 over 1 minus x. Okay. So this is a different method. This is not the sum of infinity anymore, right? So this is a different method. Sorry. So what's this? Okay, so what's this? So what's the f at a? It's just 1 over 1 minus a. Okay. And then what is f prime a? I think we computed just now. Is 1 over 1 minus x 1 minus a squared. Okay. And then what is 1 prime prime prime? Second derivative, sorry. Second derivative. Over 1 minus a to the cube. Okay. And then you can see that what do we get next? I think we get 2 times 3 over 1 minus a to the power 4, right? Is that right? Is that right? Okay. So you can see a pattern here. Negative. Just now we already discussed, right? Because there's a negative from the power, and then from the chain rule also got a negative. So negative, negative, you get positive. You see, your friend already score you already. Okay. 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 For your sake, I do one. So if you differentiate this, right? Okay, what do you get? Is 1 minus x minus prime, which is equals to what? Minus 1 times minus 1 minus x minus 2. Okay. Okay. So what's the, can you see formula from this x to the power n? Can you write down a formula for it? What is f to the power n at a? It is n factorial over 1 minus a to the an plus 1. Is that right? So if it is 0, then you got 1. If it is 1, you got 1 over 2. Okay, this is correct. Right? This is the formula. Okay. So if you plug this into our Taylor series formula, what do you get? You get fx equals to the sum of n equals 0 to infinity of n factorial over 1 minus a times n plus 1 to the Sn, which is what? Sorry, this one is centered at 0, right? Okay, so we need to center at a. So need to center at a, we need to plug in x minus a. Okay, so what's this? This is just what? This is just what? This is just what? Just what? What is this? We need to divide by 1 over n squared. Okay, what's this? This is 1 over 1 minus a to the power n plus 1 times x minus a to the power n. Okay, so what's this if I write it down term by term? 1 over 1 plus a plus 1 over 1 plus a squared times x minus a, then keep going. Okay, and then this is 1 over 1 minus x centered at a. Okay, so if my a is 0, does this reduce to the geometry series? When a is 0, okay, does this reduce to the geometry series or not? All right, right. Okay, yeah. Okay. So when a equals 0, this reduce to the geometric series. Okay, so what is this equality really doing, right? Okay, let's draw some graph. Okay, we will stop after explaining this. We still have 10 more slides. We will continue next time. But the most important one is this kind of example. Okay, so let's say this is our f. Okay, this is our f. Okay, this is our f. Okay, so what are these doing? Okay, what are these really doing? So 1 over 1 minus a, right, is just a what? Okay, let's not talk about 1 over minus a. Let's talk about fixed center at 0 so that we can have easier discussion. So let's just look at when a is equal to 0. So it's this point here. Is this function here? Okay, so I plot out this function here. I'm not sure it's correct or not. I hope it's correct. So let's say this is correct. So let's look at the point s equals 0. Okay, the function looks like this. Okay, and then the radius of convergence is minus 1 to 1. Okay, what does this mean? Okay, so when x equals to when you just look at the first terms here, 1. Okay, how does 1 looks like? 1 is just a straight line. Okay, maybe it's just something like this. Okay, how about x? X is something like this, right? Okay, but let's look at what is x plus 1. Okay, x plus 1 means I shift out the x by 1. Okay, can you see that there's some, you see this line here go closer to the original function than this line. I mean, okay, wait, let me, you get down. Okay, this is y equals to 1. Okay, this is fx equals to 1. Okay, let's call it f1 then. f1. Okay, let's call it x1. Follow your notation in the lecture note. So x1 is equals to 1. Okay, x2 is equals to 1 plus x. Okay, you can see that this line here bends toward your original function. Okay, what can you imagine is you add more terms, right? You can have the function approximately closer to your original function. You don't believe me? Okay, let's do S3. Let's do S3. So let's do S3. So S3 maybe is getting closer. I'm not sure what's the shape, but let's do what I want. So S3 is equals to 1 plus x plus s cubed. Okay. Morally, when you add more terms, the part between minus 1 and 1 here get closer and closer to the function. Okay, that's why we put this equal sign. So it converge. Okay, so it converge. But away from minus 1 and 1, it can do stupid stuff. Okay, very stupid stuff is possible. That's why, very important, I want you to write down the radius of convergence. Because outside the radius of convergence, it can do really stupid stuff. Okay, it will really diverge a lot away from the radius of convergence. Okay, so let's say, for example, the e to the power x, it converges everywhere. Okay, just now we got e to the power x, right? So what does this mean? So if it converges everywhere, okay, what does it mean? It means that if you add up all the terms, okay, your function really converge. So you got this, maybe you got this, and then you got this, and then so on. Okay, and then it will slowly converge to everything. Okay, when you consider more and more terms. Okay, so this is the power series representation. Within the radius of convergence. Okay, but for EX, we know that the power series converges everywhere, right? Yeah, so So meaning if you add more and more, so okay, so let me do it again. Last. So maybe you do this. So the first one, and then the second one, and then the third one, and then the fourth one, and then so on, so on. You can see that the sum, when you take more sum, it converges to the real EX. We did a radius conversion, but for EX, the radius of conversion is everything. So you converge everywhere. You converge everywhere. Okay. Okay. Why blur that one? You blur already. We can talk again next time. Okay, we will revise again. Okay, we can revise again next time. Okay. Yeah, we can revise again. Yep. The most general one will be given the Taylor series. Later, I will do the announcement and then I upload the formula sheet. It's the same. You just substitute A equals to 0. Okay.
It is what.
Okay. 你继续说。